Hello and welcome everyone. So this is Fluid Mechanics and I'm Engineer Ronjan Argami. So our topic for today is analysis of dams. So for our learning objectives, at the end of the session, students will be able to first relate to various forces acting on a dam and then apply concepts of law of pressure, unit weight, hydrostatic force in calculating various forces acting on a dam. And then perform analysis of dams, and then evaluate the factor of safety and pressure distribution on dam structures. Forces in dams. Defining dams, dams are structures that are built which serves as barriers to impound water. So the analysis is that we are going to take a unit strip, either 1 meter or 1 feet, when dealing with SI or English units. The forces in dams, first we have P, wherein P here is the horizontal force on the vertical projection of the unit strip. So the application of hydrostatic force on plane surfaces will be applied here. And then W denotes all weights that are transmitted to the base. Next we have U, uplift force. These are upward water pressure due to permeability in the supporting soil, meaning the tendency to sip and escape under the base. Then we also have here the silt pressure force. These are muddy flows along the bottom of the reservoir. So silt pressure forces are normally indeterminate in its location. So these are silt or clay deposits. So it has no considerable effect in its stability. So silt pressure force here is neglected in our analysis. Note, include buoyant force as an uplift force. So to illustrate that, the analysis of dam, let us say we have here a gravity dam with an upstream phase, well, the upstream will be the source. So opposite to that is normally the toe. Remember that the toe is the pivot of the dam structure. And along the side of the upstream is the heel. So on the other side, we have here the downstream, wherein the impounded water will be released on the downstream. So first, we work on the horizontal forces on the vertical projection of the unit strip. So of course, we wanted to denote our head on both sides of upstream and the downstream side. Let us denote our upstream head as H1, wherein we are going to consider 1 meter strip of the length of this dam. Now out of that, by the principle of hydrostatic force on plane surfaces, we'll just have to project that vertically. And below the center of gravity is the center of pressure, wherein the horizontal force will lie. So PH1 is given by the formula gamma H bar 1 A1. So this is a concept previously. Similarly, we are going to label also our head on the other side, on the downstream side. So let us say that this head is H2 and a strip of 1 meter is considered here. Then we have the hydrostatic force towards the dam. So let us say that this is the horizontal component of the hydrostatic force along the downstream pH2. Now pH2 is denoted by gamma H2 bar area of 2. So area of 2 is considered as the rectangle. And that rectangle is 1 meter strip as mentioned a while ago. So next, we work with all weights that are transmitted to the base. So of course, this dam will be subdivided into composite areas. So on the crest of the dam, we have here a rectangular shape, and on that rectangular shape, we'll have the center of gravity, where the concentration of the weight is located. So we can also consider a spandrel. So this spandrel shall have its corresponding center of gravity. Likewise, on that center of gravity, its weight is located. You can also consider another rectangle here, center of gravity, and the corresponding weight of this rectangle. So we label that force as weight 3. Now to complete the weight of the dam structure, we have the base of the dam in rectangular form. So this rectangular form likewise has its center of gravity. So from that, it has its corresponding weight, say W4. So aside from the weight of the dam, we also have the weight of the liquid that is being transmitted at the base of the dam. So of course, similar procedure. We are going to project the liquid that are being carried by this dam up to the liquid surface. So in here, we have a rectangular shape. So this rectangular shape has its center of gravity, wherein the weight of water is also located. Say this is W5. Also, we have space here underneath the crest between the spandrel portion. We have the weight of water. And this parabolic shape will have its center of gravity with its corresponding weight, say W6. So because of the head present on the upstream side, there will be a corresponding pressure that will be developed on the heel. Say that is gamma H bar 1, and the other one is gamma H2. So the pressure is measured by gamma H, gamma H1, and gamma H2. So we have lesser value for the pressure at the toe since it has lower head comparing to the upstream portion. So notice that we will have here a trapezoidal pressure that will be developed on the base of the dam. So we can subdivide that trapezoidal pressure. First, we have a rectangular, has its corresponding center of gravity. The uplift force, say U1, and then we work on the triangle shape. The triangle shape has its corresponding center of gravity of that one, wherein the second uplift is concentrated. So note here that this overhang of the crest will be considered as subject for buoyant force. So again, we get the center of that one and then place here U3 or the buoyant force of that overhang. as if this moment we are going to focus ourselves on the toe. So this toe is the pivotal location of the dam with the effect of the uplift force, the hydrostatic force, and the weight. So first, it will cause a couple on the toe because this is the pivotal joint. So this tends to overturn the dam, so it is called as OM or the overturning moment. So opposite to that direction is also another couple that is righting moment or the restoring moment against the direction of that overturning moment. To work on this OM and RM, we need to determine the distances of all of the forces to the toe. So W1 will have its corresponding distance from the toe, say this is x1. W2 will have its x2. Likewise for W3, W4, W5, and the weight 6. So note here that those distances are measured from the center of gravity of these composite areas up to the toe. The uplift forces also have its corresponding distance from the toe. Say XU1, and for U2 we have XU2, and for U3 we have XU3. For our hydrostatic force acting horizontally, this distance is actually Z1 and it's given by the expression H1 all over 3. So whatever the height or the head of that side, we'll just have to divide that by 3 on the principle that this submerged plane surface is totally submerged into the water. And the pressure is in triangular form, wherein it is 0 at the liquid surface and at maximum at H1. Likewise, for the downstream side, we have Z2, distance of the hydrostatic force from the toe. So we simply divide our H2 to 3 to locate this PH2 from the toe. So all of the vertical forces will have its corresponding resultant. And this resultant shall be opposite to the prevailing force vertically. So this vertical force will be denoted as RV. Like RV, likewise, will have its corresponding distance from the two, say x bar. So on the horizontal axis, horizontal forces will have its corresponding resultant, say RH, and that RH should be oppositely directed to that of the prevailing horizontal force. Say this is RH. Now that we have labeled all necessary distances, forces, and notations, first we are going to perform equilibrium equations along the vertical direction. So summation forces vertical is equal to 0. We sum all the vertical forces. RV is going upwards. All the weights are going downwards, denoted by negative. And the uplift forces will be upwards, denoted by positive. Hence, therefore, the resultant force along the vertical is equal to the summation of weights less the summation of the uplift forces. Number 2. We perform equilibrium equations along the x-axis. Summation forces horizontal is equal to 0. So your assumption for RH is towards leftwards, therefore denoted by negative, and then plus going rightwards PH1 minus going leftwards PH2, all will be equated to 0. Solving for RH simply the difference between the, the hydrostatic force of the downstream to that of the upstream. Number 3. So we determine the overturning moment. So the overturning moment are all the forces that will cause a couple along the direction of the overturning moment. So remember that the overturning moment is the direction that tends to overturn our dam. So performing that, OM is equal to the upstream horizontal force times its distance from the toe, and then the uplift with its corresponding distances from the toe. Number 4, writing moment. So this is also summation moments, the toe, considering only those forces that will cause a couple along the direction of the writing moment. Hence, the writing moment will have pH1 times Z1 and all the weights with the corresponding distances from the two. Number 5. Summation moments at the toe is equal to 0. This is to satisfy equilibrium, meaning the dam will have no rotation at all. So we equate the resultant force along the vertical times its corresponding distance to the toe. It will have a clockwise direction moment. And then we add the overturning moment, which is also along its direction. We also less the writing moment against the direction of overturning moment, that is counterclockwise, is equal to 0. So here we can locate the vertical resultant that is intersecting the base of the dam. So this is equal to writing moment minus O overturning moment all over the vertical resultant. Number 6. Factor of safety against overturning. So this is denoted by Fs sub O. So we always wanted that the writing moment is always greater than the overturning moment. Hence, the formula is simply Rm all over On. Number 7. Factor of safety against sliding. This is denoted by Fs sub S. This is equal to mu Rv all over Rh. Basically, we use the resultant force along the vertical and the horizontal, where mu is the coefficient of friction between the dam and the supporting soil. So at this moment, we have already determined the procedure, presented the procedure wherein RV shall be located anywhere in the base with X bar. So X bar is referred from the toe. So the resultant along the vertical will have a pressure effect at the base. So basically, there will be a pressure distribution at the base. For a good design, RV should be within the middle thirds. So what is the middle thirds? So if this is the base, we'll just have to divide that into 3 segments, where in the middle zone will be the middle thirds. So case 1, when RV coincides with the center of the base. So if this is the base, the red portion is the zone of the middle thirds. Of course, these segments are equally divided, b all over 3. So in here, our RV is coinciding the midpoint of the base with the X bar. Of course, X bar is automatically be equal to b all over 2. Hence, the distribution will be in uniform pressure. Why? Because RV is pointed on the center of our base, which is a rectangular base. So this is the base pressure. Therefore, from the formula of the pressure is equal to force all over area, RV is equal to the force or the pressure at the base times the area, which is B times 1. So the base area is actually the unit segment or 1 meter segment or the strip times the width of the dam. So basically, RV emanated from the formula that force is equal to pressure times the area. So solving for the pressure, this is equal to RV all over B. So this is the base pressure for case 1, where RV coincides with the center of the base. Case 2, when RV is within the middle thirds. So if this is our base with the middle third zones, so RV will no longer be exactly at the midpoint of this B. So RV is referred to X bar from 2. Okay, of course, we will have a base pressure that will be developed. So in here, the location or the edge where RV is nearer, we have a larger value for the base pressure. That is why it's called PB maximum. On the other hand, the edge with farther distance to RV, we have the base pressure minimum. So when we project that, we'll have a trapezoidal pressure that will be developed at the base of the dam. So of course, when RV is not within the midpoint of the base, therefore, there will be a certain distance of RV to make it eccentric to the neutral axis. Say this is the eccentricity E. So therefore, the base pressure is equal to force all over area, RV all over A, plus or minus. Plus is used for maximum, minus when the base pressure is at minimum. So we insert the formula or add on the MC all over I, because MC all over I is a flexure formula. So the first term is the formula for base pressure, and the second term is the formula for the flexural pressure, wherein the moment couple developed is out of the force RV times the eccentricity from the neutral axis. So C here from the formula will be the farthest distance of the neutral axis to the outer fiber, which is B all over 2. Remember that when we view our base from the bottom, it will be in the form of rectangular form, wherein the neutral axis is half of the base. So the moment of inertia is given by the formula BH cubed all over 12 for a rectangular section. So when we use this formula, of course, this is along the longitudinal section, wherein the base will be the 1 meter strip, and the height will be our width. So therefore, we have B cubed all over 12 for our moment of inertia. And for the area is 1 times B. 1 meter strip times the width. Therefore, the maximum base pressure or the minimum base pressure is equal to RV all over the area, which is 1 by B, plus or minus. Our moment is RV times E. Our C is B all over 2, divided by the moment of inertia. Manipulating the equation, we simplify the second term. We have RV times 6E all over B squared. Notice that RV all over B is common to the terms of the equation on the right-hand section. So therefore, the maximum pressure and the minimum pressure will be equal to RV all over B. What is left is 1 plus minus 6E all over B. So this will be the formula for maximum or minimum pressure at the base of the dam when RV is within the middle thirds but not coinciding with the center of the base. So this is all about the concepts of the analysis. First, we have Fs factor of safety against overturning, factor of safety against sliding, the location of RV, and the pressure distribution at the base. Thank you and have a good day.